So, good morning, everyone. Today's talk will be by Nikos Melissinos, and it will be on the odd chromatic number of graph classes.
Thank you for the introduction. I am Nikos, and I will present you this work. It's a joint work with Rémi Belmonte, Arad Harutnian, Nolin Kohel, and me. So we're going to talk about odd chromatic number, but what is an odd and what is an even coloring? The definitions are similar between the odd coloring and even coloring, so I'm going to say only the things about the odd coloring. So a graph is odd when all the vertices have odd degree. So basically you can imagine something like a complete graph with 4 vertices. Then each vertex has degree 3. So this is an odd graph. And what is a k-odd colorable graph? Is a graph where you can partition the vertex set into k sets. So each set induces an odd graph. And the odd chromatic number is the minimum k such that the graph is k-odd colorable. Some examples here. You can see here a path with 4 vertices. Then I can color 2 vertices with blue, 2 with red. You can see that all of them have degree 1. So that's odd, 2 odd colorable. This is a complete bipartite graph, and this is a cycle. So you can check the degrees, and all of them are odd colorable. Okay, so what it is known. One of the first results related to odd and even chromatic numbers is one of Gallai, from 60s or something. And the result was that you can partition any graph into 2 sets such that those 2 sets are both induce both even graphs. And another result of that period was that you can partition against the vertex set into 2 sets such that one set induces an odd graph and the other an even graph. This gives us the result that any graph is 2 even colorable, and we can easily check the even chromatic number of a graph because you can just check whether it's 1 even colorable by checking the degrees. So this gives us some questions regarding the odd coloring. So are all the graphs odd colorable? That's an interesting question. And also, because you know that every graph is 2 even colorable, does the same hold for odd colorings? I mean, is some constant that bounds the odd chromatic number of any graph? Okay, so since 2001, it is known that not all graphs are odd colorable, but if we have a connected graph of even order, then we know that is always odd colorable, and the reverse. If a graph is odd colorable, then it must have even order and should be connected. Yeah.
Even order is what exactly?
In order?
Even order.
Yeah, even order.
What does it mean exactly?
The size of the graph is even.
Oh, okay.
Yeah. So now the other thing is that the number of colors also is not necessarily bounded, because you may have graphs with a huge odd chromatic number, and I'm going to use this k odd, chi odd, how it's called in English, the chromatic number with the odd below, indicating the odd chromatic number of a graph. And this could be also a square root of the size of the vertices. And the example comes from a subdivided clique. So start from a clique, subdivide all the edges, and then you can observe that 2 of the original vertices cannot have the same color, because those subdivided vertices, those here, now they can either share a color with those 2 vertices and have degree they have two vertices of the same color, so it's 2, so it's never gonna be odd colorable, or 0, so again it's never gonna be odd colorable. So the original vertices must have different colors, and this gives us a number, a bound of square root of n, a lower bound. So neither we have a constant such that any graph can be colored with a constant number of colors. Okay, so what is also known now is that, okay, this square root of the number of the vertices, it should be huge number, and we could have some results about that, but unfortunately the only known upper bound related to the number of vertices is this huge upper bound, which is a constant number of vertices over the square root of log number of vertices. And some other interesting results is that any graph, all co-graphs need at most 3 colors. Graphs of bounded trig width need at most the number of the trig width plus 1 colors. And finally, subcubic graphs and plural graphs need at most 3 colors. Now, if you relate this with the previous observation that we have, well, we don't have actual examples where we need more than square root of n colors, and no graphs that require more than maximum degree plus 1 colors, then this leads to 2 interesting conjectures that already stated by Scott 2001. So the first conjecture is that probably no graph gonna need more than square root of the vertices colors, and the other one is probably we not gonna need more than maximum degree plus 1 colors. So what we try to do here, it was addressing some of those questions in regards to graphs with bounded degree, graphs with bounded modular width, and interval graphs. And let me start with the graphs of bounded degree, which is probably, in my opinion, the most interesting question because it's related to the conjecture. And what we managed to show is that, okay, we don't know if the maximum degree plus 1 is enough, but we managed to show that 2 times the maximum degree minus 1 is enough. And to do so, we proved something much more complicated, or that's how it seems. And we saw that any graph class which includes the clique with 2 vertices, it is closed under vertex deletion. And we can always have either 2 vertices where the addition of their degrees is at most k, or 1 vertex with 2 leaves, then this graph is always k minus 1 colorable. So how we did that? Well, this was based on induction, so k2 is 1 colorable, perfect. Then what we are doing is assuming that we have colored all the graphs with order 2m, then we will use induction and consider 3 cases. One case we have 2 leaves. Second case, we have 2 vertices that there's the sum of their degrees is at most k, and the remaining graph is connected, or the remaining graph is not connected. And how we deal with those things. So first, the case with the 2 leaves. This is a really easy case because we can just delete the 2 leaves here, color the rest of the graph. Because it's connected, we know that it's colorable by the induction hypothesis. And then we are coloring those 2 with the same color as the neighbor. This doesn't change anything for the rest of the graph. And because this should have odd number of the same color neighbors, it still has odd number because we just add 2. So now the second case is when you have those 2 vertices that the sum of their degrees is at most k, and the remaining graph is connected. Then again, we deleted those two vertices, color the rest of the graph. And then what we are doing is putting those two vertices back and give them a color that does not appear in the neighborhood. Observe that, again here, well, this should be k minus 3. K minus 2 is okay, sorry. So here it has k minus 2 vertices, so they saw at most k minus 2 colors, so one extra color it always remains to color them. And then we have the case where the remaining graph is disconnected, and here we need to consider two cases. There exists a component that's of even order. Then what we are doing is separate this component from the rest of the graph here, and color this one, not necessarily with one color, but I using two different colors to distinguish that I'm coloring this alone and the rest by itself. And then I need to combine the two colorings. And again, here, this red part has at most k minus 2. Here it was k minus 3. Because it's disconnected, it means that there's at least one extra edge here. So it has k minus 3 vertices that sync both of those two. And because it's k minus 3, you have at least two colors that they can be used. And I don't know whether those two are going to have the same color or not, but again, we have enough colors. Finally, if all of the parts are of odd order, then we need to partition them in some way. So basically, we have some of those that are connected only to V1, some others that are connected to both of them, and some that are connected only to V2. And basically, we try to color the parts based on V1 and V2. Okay, we need also to decide whether those are going to be with V1 or V2. But when you partition all of those, then you can combine the colorings, and because we have too many components, again, the degrees are enough in order to not having any problems. So this completes the previous proof, and if you consider k to be 2 times the maximum degree, then you have the result about the maximum degree I was mentioned above. And this is also has another corollary, which is that graphs with large girth, if the girth is at least 7, then the odd chromatic number is at most 2 times, 3 times. 3 times square root of n over 2 plus 1. And this basically comes from a counting argument when you can consider the girth, count the number of vertices that appear, and you manage to show that there exist 2 neighborhood vertices that always have this upper bound of the sum of their degrees. And using again the previous theorem. Okay, so then we considered graph of bounded modular width. And let's discuss a bit what exactly is the modular width of a graph. So this is defined as follows. If you have one vertex, this has modular width 1. And if you have a graph and you can partition the vertex set into k sets, and each one of those sets, the graph induced by this set has modular width at most k, then the new graph also has modular width k. And usually we are calling those partitions or module partitions, etc. Okay, so what we wanted to show is that this number k give us the upper bound. So basically, any graph of modular width k, it requests 3k colors in order to be colored. And the idea of the proof is based in 3 facts. The first one says that, okay, we can partition a set into 2 sets, a graph into 2 graphs, so that both of them are even. This was from Gallai's theorem. The second one is the second dot from Gallai's theorem. You can partition a graph into 2 graphs, one odd, one even. And the final one is that you can partition into 3 parts. And you need to play a bit with the order, if it's odd, if it's even. It's not extremely important, but you can partition it into 3 parts. Now, so what exactly happens then is this is basically the probably I'm running too much. Okay, so probably this is one of the first steps for our reduction, where you can consider that the graph is a star. If the graph produced by the modules of the modular width is a star, then we can deal with all of those based on those partitions that I will mention. And let me a bit take a step here and explain. So you have some leaves of odd order, and you partition them into odd and even graphs. You have the middle vertex of the star, also partition it, and you partition also the even leaves, and then you need to combine appropriately those partitions, because here you have some even partitions, and those even partitions must be of odd size, because otherwise these leaves are not of odd size. And if this is a odd number, then you can combine them with the even part. So now this even part will have odd number of neighbors, because it has odd number of times. And here those parts are both of even order, because this was of even order, the odd parts must be of even order. So you combine them with whatever you want. So those all the evens are okay, and then you need to keep those odd parts by themselves. You don't really care, and because they are not connected, you can do it with 3 colors. Sorry, probably even with 2 colors. This first one. And similar ideas you are applying in the second and third case, where based on the exact number of vertices, you may need to do these weird things where you need to partition it 3 times in some cases. Okay, the second step, it is that we create a weird tree that's called color propagating tree. Basically, this is imagine that all the modules are in the leaves of that tree, and every other node is just one vertex inside that. We managed to show that if we have such a construction, then we can use at most 2 colors. I'm not going to go in the details how this is exactly be done. And finally, we saw that if we start from any graph, then we can partition it such that one of the partitions have at most k-1 modules. So we have reduced the number of modules. And the other part of the partition is either a star or a propagating tree. Now, because the star in some cases needs 3 colors, if you repeat this thing, you can find this upper bound about 3k. Okay, so after finishing with that, we try to see other classes, and an interesting class here is the interval graphs. So the definition of the interval graphs, for those that are not familiar with, the interval graphs are defined as follows. You have intervals. Each interval represents a vertex. And if 2 intervals intersect, then you have an edge between those 2 vertices. Also, we have proper interval graphs, where the proper interval graphs, you know that no 2 intervals include one in the other. So you don't have an interval as a subset of the previous interval. Okay, so we managed to show that proper interval graphs need at most 3 colors, while the interval graphs are needed at most 6. And the idea, at least for the proper interval graphs, which is easier to explain, is that you just need to define a huge path. You're taking a maximal path where and a maximal induced path. And then you are defining cliques of the proper interval graph based on those vertices, and you try to give the colors, one color in the first click, second color in the third, second color in the second, third color in the third, and then you start repeating colors. So for those that are a bit familiar with proper interval graphs, the image is something like this. The path that we're creating is basically has one vertex from the first click, then the second vertex in the intersection between the first and the second click, the third vertex in the intersection between the second and the third, etc. Then the vertices that are not in the path can be colored with the way I was explaining before. So we're using three colors here. The first color, the second color, the third color, and then we are going to start repeating colors. And we only need to decide what we are going to do with the intermediate vertices, and those are just in order to decide the correct parity. So basically, if this first part here is odd, then we need to color this P2 with the same color in order to be even, because a click of even size is odd colorable with one color. Perfect. And continue repeating the same thing. And because of the parities, because all of those are going to be even, then the last part is also going to be even, and we don't have any problems. Okay. Probably I was running, like I said, because now I'm starting to conclude. So what we managed to show is that graphs of bounded degree request at most 2 delta minus 1 colors. Graph of bounded modular width requests 3 times the modular width. Interval graphs, for the interval graphs, let me study. Basically what happens is that you can define again some path like this one, but you also have some weird other vertices outside of this, and basically you need to split those parts in 2 or 3 parts in order to verify the degrees. But the idea is similar but much more technical in order to prove. So okay. So proper interval graphs with proper interval graphs 3 colors. And some open questions. First of all, both of the conjecture are still open. We managed to show that 2 delta minus 1 colors are enough, but we don't have any example that requests delta plus 2 colors. So this is still interesting to see if the correct upper bound is delta plus 1. And also for the vertices, the square root of n seems convincing. We don't have examples that this is not true. Okay, so also for the interval graphs, we have this upper bound for 6 colors, but we couldn't find an example that requests 4. We try a bit. We couldn't be sure how to deal with this and managed to force a 4th color. So maybe the 6 is also reducible. And finally, one interesting question is graphs of bounded rank width. This is interesting because for rank width, there exists an algorithm that is FPT by rank width plus the number of colors. So if we manage to bound the number of colors, then we have FPT algorithm only by rank width. So this could be also something that interests. And let me close with a nice image where we have most of the known results. I don't know if something is missing. So this color represents graph classes that have bounded odd chromatic number, and this one, and those two are the ones we proved in this word, and this one also. Those are open cases, the orange. The blue one is a graph class that we know that the conjecture is true. Well, also the green ones, but those were already known, for example. And here we have some classes that we know that request at least square root of the number of vertices colors, which is split graphs and cordon graphs, because this is coming from the subdivided click. Thank you very much.
Thank you, Nico. Do we have any questions?
You mentioned the FPP algorithm for rank width together with the number of colors.
Yeah, it exists an algorithm from rank width plus the number of colors.
Yes.
So
and is this the best known or is it something like even like twin width or something?
I don't know something. So
Any other questions? I have a question. Planarity. Is any work done on planar graphs for
Yeah,
those?
actually, I mentioned that at
Sorry.
some point.
It was there.
Yeah, it was somewhere in the start.
Okay.
I don't find it. Okay, so it requests three colors. Yeah,
Okay.
subcubic graphs and planar graphs.
Okay. Any other questions that were not already covered?
So, for normal coloring, this also holds for planar graphs. Degeneracy is the decisive parameter somehow. So, does degeneracy do something for mod coloring?
I don't know. To tell you the truth. Not sure.
Something like three width is two digit. Yeah. I mean, the subdivided click is two digit, so.
Yeah.
Thank you. There was another question, I think. No?
Oh, well, that was just my thought. So there are inequalities between the high odd and graph classes, but surely some of them are equalities, right?
Sorry.
So some of these inequalities are probably equalities, aren't they?
Well, yes. Many of them. Well, I have inequalities because some of them can be colored with less colors. So not all graphs request that many colors. But those inequalities, we have graphs that, well, not the first one, obviously, but for the rest,
that was I was like looking at the worst case in the given graph class.
No, I don't think so.
So there is no co-graph that requires split color.
Oh yeah, the worst case, yes, there are co-graphs. That's what I was saying before. That no, I thought that every co-graph requires.
No.
No.
My question was if there is some graph class where
Yes.
this gap is not closed.
There are.
Only degree. Only.
So if I'm correct, so for the planar graphs, the planar graph that means at least three colors is the subdivided case tree, right?
Yeah, for example,
So
it
planar
was
graph
here.
is three.
Any other questions? Okay, so let's thank Nikos again.